Hello, class. Okay, so in this lecture, we're going to talk about the relation between electric potential and electric fields. So I mentioned before that there is a relation, a very important relation between them. And so I kind of have a setup here already drawn. And what we're going to do is, let's say we have a charge Q. I made it a positive charge just to make things make things easy. Let's just make it a nice 1 microcoulomb. Okay. And then a certain distance x away from that we have a point A. And say we want to know the electric field at point A. Well, we already know that because we know the electric field. We can write KEQ over R squared. In this case, it would be KEQ over X squared because that's the distance. And we know it's along this direct line connecting them. So we already know the answer to this question. But we're going to do it a different way. And the way I'm going to do this is kind of just write down the answer, like show you the connection, and then kind of show that it works. So we want to know the electric field at point A. So what we're going to do is I drew a point B that's a distance delta x from A, and I drew a point C, a distance delta y, in the y direction from point A. And we want to say that delta x and delta y are small. So the idea is we want to know what the electric field is at point A by looking at kind of the region around A. Like we're going to look at what happens if we go a certain amount delta x in the x direction or a certain amount delta y in the y direction. And what's going to happen to the electric potential? Like how are they going to compare between points A and B or points A and C? And I'm going to write down that result and then try to justify it. So let's see, at point A, I'm going to write down at point A, what I'm going to say is the electric field at x, the x component of the electric field, I'm going to say that's approximately equal to minus VB minus VA over delta x. And the y component of the electric field is approximately equal to VC minus VA over delta y. So basically what we're looking at is changes in electric potential, like say in the x direction. Like point B is a distance delta x in the x direction. And so what I'm saying here is that the electric field in the x direction, it's related to the difference in potential between these 2 points divided by that magnitude delta x. Now, why is there a minus sign here? Well, we know that the potential decreases as we get farther away. So we know that the potential at B, let's look at VB minus VA. We know just from the definition of electric potential, because we have a positive charge, VB minus VA is negative. It's less than 0. VB is a smaller number than VA. Just, we divide by a bigger R. And we know the electric field is pointing to the right. And so if we put this minus sign here, that'll give us the electric field pointing in the x direction. Now, again, I hate to do this. I hate to just write down formulas and say, here it is. But I can actually justify this. One more thing, I'm not going to write this down because we're restricted to a 2-dimensional graph. But we could also, I'll write down the formula anyways. I'm not going to try and draw it though. The electric field, it has 3 components because it exists in 3-dimensional space. Let's say we have a point D. which again, I can't draw point D, but point D would be like coming away from the board, a certain distance, delta Z. So we divide by delta Z. So again, you can get all the components of the electric field by looking at the electric potential in a region around the electric field. Now, why do you believe that these formulas are correct? Now, we can kind of check this, and we're just going to look at the x direction, and I've got a table which is in the notes, but basically we look at, let's say x is 1 meter. I'm going to double check this. Or no, x is 1 centimeter. Yeah, I'm going to look at the notes again. I kind of mixed up the units because in the written description it says 1 coulombs, but I wrote 1 microcoulomb. So I'm going to have to check that and fix the notes. But I made a table where we have a couple things. First column is delta x, which I started out with delta x being fairly large, like 1 meter. And then I'm not going to fill out this whole table, but it gets down to we can make delta x starts out relatively large. Yeah, I think x was 1 meter when I was doing these calculations. So this point is 1 meter from the charge, and we make delta x a full meter. And then I showed some intermediate steps, like the potential at B. The potential at A, I didn't put in the table because A is a fixed point. So VA is just some known thing. So the next thing we have VB minus VA. So again, the potential at B depends on what we pick for delta x, but the potential at A is just a fixed number because x is fixed to be, I believe, 1 meter, even though I wrote 1 centimeter. So I'll check the notes and kind of make a comment about that. But yeah, so we've got this numerator here. And then if we divide by delta x, so we've got VB minus VA divided by delta x. And again, and then we filled out all these numbers, which we can do just by looking at electric potentials. Now what we can also do is use this formula to calculate the electric field at point A, because we know the charge and we know x is a fixed number in this case, so that would be r. We know the charge, we know the constant, we know r, so we can find the actual electric field. And I'm going to just, obviously look at the notes, but for now I'm going to calculate, right, let's see. I'm going to write down the actual value of the electric field at point A. And I went to way more significant figures than we normally do. Well, let me just write that down. Okay, so 8.987552 times 10 to the 9th newtons per coulomb. So that's the actual electric field at point A. And what we're calculating is basically delta V over delta X. Or here, let's put the minus sign in front. So we're calculating VB minus VA over delta X. And again, we have this approximately equal sign. So I'm going to hold this up and see if you can see the numbers at all. But in this start, we have delta X is 1 meter, which is very large. And what we get from delta V over delta X, that's at like 4.4, it's upside down when I'm looking at it, but yeah, like 4.493, if we pick delta X to be 1 meter, then what we get from delta V over delta X is way off from the actual electric field. But you can see if we make delta X smaller, if we keep making delta X smaller, pick 1 meter, 0.5, 0.1, and then, just keep getting smaller by a factor of 10, you can see like on this last column that delta V over delta X, that gets closer and closer to the electric field. And so ultimately, you can make this exact by using a limit. Like we could say that EX is exactly equal to, so you would have to do this limit thing, which requires calculus. We could just write it like that, delta V over delta X. We have to take the limit that delta X goes to 0. And again, we can't actually use this because, that's calculus, using limits. But hopefully this table, again, I recommend checking the notes instead of just me holding it up to the screen. But, you can see if delta X is very small, the difference, you have to go to, let's see, about 6 significant figures to notice any difference at all between this and the actual electric field. So the smaller you make delta X, the better this approximation becomes. And in the limit that delta X goes to 0, it becomes exact. So this is a formula that shows a connection between electric potential and electric field. Now, why do we care about this? Well, there's several reasons. Like one very common thing we might want to do clear the screen. And say we have a bunch of charges. And some point P, and say we want to know the electric field here. Well, we know how to do that. We can find E1, which would be the electric field due to charge 1. Let's say Q2 is negative, so that would point in this direction. Let's say Q3 is negative as well. So I just kind of arbitrarily made up these directions. So yeah, we can calculate E1, E2, and E3, and then add them up. Problem is, we have to add them up as vectors. And so, in many cases, not something we do in this class, but it is like one very important application of this equation, is that instead of calculating electric fields, what we would do is we'd calculate the electric potential and then use that to find the electric field because there is this connection between them. And remember, electric potentials are scalars. And so a lot of times, if your goal is calculating electric fields, you can calculate the electric potential and then use that to get the field. We don't do that here, except maybe in one special case. So that's a very important application of it. Now I said we don't do that here. The one case where we would do this, say we have a constant electric field. Now, we're going to talk very soon about how we could produce a constant electric field, and that's a device called a parallel plate capacitor. So say we have 2 plates. Say one's positively charged, one's negatively charged. The electric field is going to go straight from the positive plate to the negative plate. We're going to talk more about this later. But the electric field in between the 2 plates is constant. Now, when you get near the edges, they would curve around a little bit. But if you're not near the edges, to a very good approximation, this is a constant electric field. And then this equation, I'm going to write it, I'm going to erase this actually. Just kind of start over here. I'm just going to write it like this. So if you want the x component of the electric field, you look at a displacement in the x direction and look at how the potential changes. And that's an approximately equal sign, but the smaller the delta x is, the better that approximation is. However, if you have a constant electric field, this becomes exact. So for a constant electric field, we can say that the electric field, say in the x direction, is exactly, in magnitude, it's exactly equal to delta V over delta x, whatever delta x you pick. As long as both of these points where you calculate the potential are in this constant electric field, it doesn't matter which 2 points you pick, you'll get the same number. And again, that's only true for a constant electric field, but that is a very important example. We have a parallel plate capacitor where we can say there's a potential difference between the 2 plates and see how that relates to the electric field. But we're going to do that a little bit later, so I'm not going to talk too much about capacitors right now. So that's an important special case where we can actually use this to calculate or to see exactly the relation between electric field and electric potential. But what we're going to do this for is not really calculating electric fields. There's actually an amazing amount that we can get out of this without actually using it for calculations. And before we get into that, I want to talk about 2 things. One is an equipotential. So, as you might guess from the name, equipotential means it is a region where the potential is equal. Now, generally, it could be like a 2-dimensional region. Like, say we have a point charge. We know the potential is KEQ over R. So if R is constant, if we pick some radius, like say a distance of 1 centimeter from this charge, what we would get is actually a spherical shell. So I'd have to draw it as a circle, but it's also coming out of the board. And going into the board, it's a spherical shell. But basically, this is an example of an equipotential, because wherever you are on this circle, the potential is always going to be the same, because R is the same, so you'll get the same potential. So, yeah, basically an equipotential just means the potential is equal, and very often we just draw them like lines. So I want to just define what an equipotential is, and I'm going to move this over here. Move this picture. So say we have a charge here, then yeah, this would be, actually I'm going to draw 2 equipotentials. Okay, so I drew 2 equipotentials because they're at different distances. And let's say this is a positive charge, so the voltage, we could easily calculate that if we knew the charge and the distance. Let's just say this one turned out to be 900 volts. And this one farther away is 500 volts. So again, that will be true for some charge and some distances. And it's a positive charge, so the electric field is going to point radially away. Okay. Now, one thing we can see from this, if we follow the electric field in the direction that it's going, I mean, the electric field isn't really moving anywhere, but if we just follow it in the indicated direction, we're going from 900 volts down to 500 volts. So what we're seeing is that the electric field is going from high potential to low potential. I'm going to write that down. E field goes from high potential to low potential. Now, that's with a positive charge. What if we had a negative charge? Well, if we just replace that Q with minus Q, let's draw these 2 surfaces again. Here we'd have 900 volts and minus 900 and minus 500, and the electric field would go radially inwards. Our electric fields point towards negative charges. So if we just replace Q with minus Q, we have the same magnitude, but they're now negative. So again, if we follow the electric field in the direction indicated by the arrow, we're going from minus 500 to minus 900. We're still going from high potential to low potential. Minus 500 is a bigger number than minus 900. So, yeah, even though it doesn't look like it, you can picture like a number line. So let's say that this is 0. So it's like here we have 500 to 900. And over here we have minus 500, minus 900. Yeah, like these, the numbers are just ordered, where these are higher, these are lower. So if we look at here, going from 900 to 500, we're going from high to low. If we go this way, we're going from minus 500 to minus 900. We're still going in the same direction from higher numbers to lower numbers. So that's one thing that we can see about the connection between electric fields and the electric potential, is electric fields go from high potential to low potential. And I want to write one more thing we want to talk about. I'm going to draw an equipotential. Let's say that this is in the x direction. So we have x and y. And let's say our electric field looks like this. Okay. So let's just do this. Let's look at this formula. So what we can say is that let's just look at the magnitude of the electric field in the x direction. So let's call this point A and this point B here. So we'd have, VB minus VA. Let's say that's delta x. And similarly, EY, the magnitude, let's call this point C here, where that's delta y. We'd have VC minus VA divided by delta y. Okay. Now, something might jump out at you immediately, just from looking at this. Just if it's not jumping out yet, I'm going to write, this line here is an equipotential. Maybe instead of writing that out, let's just say this line is, say, 100 volts. So like every point on this line is 100 volts. Now if we look at EX, both of these points are on the line, so what we're going to get, regardless of what that number is, we're going to get EX equals 0. And basically what we've shown here is a very important connection between electric fields and equipotentials, and that the electric field is always perpendicular to equipotentials. Okay. So like here's our equipotential, it's a line in this case. So the electric field is perpendicular, so it can't look like this. The x component of the electric field has to be 0. But it can have a y component. Like if we have another line here, let's say this is 50 volts. Well, yeah, I mean there's a change in potential in the y direction, so there will be an electric field in the y direction, but there can't be in the x direction. So yeah, this doesn't work, but the electric field can certainly look like this. And also note it goes from high to low. Electric fields point from high to low. So that's something that we can get out of this equation, that the electric field is perpendicular to the like any equipotential region. Again, look at our point charge. Remember, electric fields are radially away from the charge, and the equipotential are spherical shells, or if we look at a two-dimensional cross-section, the equipotential lines are circles. Again, these are always going to be perpendicular to each other. Like a radial line and a spherical shell, they're always going to be perpendicular to each other. Now, there's one more thing we can get from this equation. And what I'm going to do is I'm going to draw something on the board. I'm going to draw... remember, inside a conductor, the electric field is typically 0. If we're talking about like an electrostatic case. And so if the electric field is 0, what that means is that delta V is 0. So inside, a conductor itself is an equipotential. So let's say we have two conductors here. I'm going to kind of fill these in. Say we have one conductor that looks like this, and another conductor that looks like this, and these are charged conductors. And so there's going to be, in theory, we could calculate what the equipotential would look like. I'm going to try and draw some equipotential lines. And it's very unfortunate that we're not actually in class, because we can do a lab where we can actually create pictures like this experimentally. But I'll draw some equipotentials, say in purple. We're going to loop around and I'm going to give numbers to these as well. Again, this is like a fairly realistic idea of what an equipotential region could look like. I'll just stop there. I mean, we can always draw more lines. But say like we know what the potential in this region looks like. And, oh yeah, I'm going to give numbers to these as well. Let's see. Let's just start here. Let's say this is 1 volt. Stick with simple numbers. 3 volts. Okay, so I just gave numbers. And what I'm going to do is see what the electric field looks like. And we can actually draw the electric field just basically knowing what we know. We know that the electric field lines are always perpendicular to equipotentials. Remember, the conductor itself is an equipotential. So I'm going to start out with a line here. You know, it's going to be perpendicular to the surface of the conductor. And just, I'm going to draw it so that it's always perpendicular to the equipotential. Like every time we get to an equipotential line, just make sure that they are perpendicular. So I'll draw several lines. Yeah, it's kind of a neat lab where we can actually find equipotentials and draw them, but doesn't work out too well like in a simulated lab, so can't really do that. I'll draw one more line. Maybe I'll have to like weave the board, and looks like it'll work out. So yeah, it is every time we cross an equipotential. We're perpendicular. Oh yeah, one more thing I definitely want to say about equipotential lines is we'll never have a situation like this. Equipotential lines can never cross each other. Reason why, let's say this is a 9-volt line and that's a 7-volt line. If you look at this line, it's like every point here has to be 7 volts. Every point on this has to be 9 volts. If they were to cross, it's like we're saying that that point has to be at 7 volts and also at 9 volts, which make no sense. You can't be both 7 and 9 at the same time. So yeah, equipotential lines never cross each other. I guess another issue, if they cross, the electric field is always perpendicular, so they'd point in different directions as well. So yeah, equipotential lines never cross. So if we know what the potential looks like, we can draw the electric field. We can also draw directions for the electric field. So remember, electric field, they go from high potential to low potential. So they're basically going in this direction. So it gets higher potential over here, like 7. So we're going from high potential to low potential. We can see what the electric field would actually look like. You can draw one more line just because there's a big gap here. And just make sure that they're always perpendicular everywhere. Okay. But there's one more thing we can say about this. We can draw a couple of points. Let's say point A and point B. And what can we say about the strength of the electric field at these 2 points? And because I can't really ask this question since this is pre-recorded, I'm just going to tell you the answer. The electric field at A, we're just looking at magnitudes. We know that has to be greater than the electric field at B. Why? Well, let's say we want to approximate the electric field at point A. We can say this is approximately equal to delta V over delta X, where delta V is 1 volt. And delta X is maybe let's say electric field at A is approximately equal to 1 volt over, say, 4 centimeters. Just like the distance between those 2 lines. That'd be a reasonably good approximation. Where at B, we've got to look at this distance, which is like 25 centimeters maybe. So we can say the electric field at B is approximately equal to 1 volt over 25 centimeters. Yeah, it's the same potential difference from 5 volts to 4 volts. That change is 1 volt, but you have to do it over a much greater distance. And so the electric field at B is a lot weaker than the electric field at A. So yeah, if you can look at the electric potential, which are these purple lines, it's very easy to see the direction of the electric field. It's always perpendicular and going from high potential to low potential. And again, we also know the strength by how closely spaced these equipotential lines are. So like here where they're close together, the field's kind of strong. Here where these lines are really spread out, like in these regions, especially over here, the electric field is much weaker over here. So yeah, the idea is if you know what the potential looks like, you also know the electric field. All right. Yeah, so I think that'll be it for this, this lecture. Now, I have a worksheet. Actually, I think I'm going to post the worksheet to the next module, because the next topic we're going to talk about, we're going to go back to talk about electrical potential energy. We're going to see a little more carefully how electric potential and electric potential energy are related to each other. And so I have a worksheet that's actually a really nice worksheet because it covers pretty much an entire chapter almost. But I'm going to post it in the next module because it does involve a question or two about electric potential energy. And again, this is just a practice worksheet, so I'll post the worksheet and the answers, like an answer key to it. So again, just for practice, but I highly recommend doing it because it really covers everything from this chapter on electric potential. And yeah, I think almost everything in that chapter. So if you can go through that worksheet, you're in pretty good shape for covering that material. But yeah, the next topic is electric energy. And so I think I'll post it to that module. Okay, so that'll be it for this one.